students, myself Dr. Divya, Assistant Professor at Department of Chemistry, Institute of Analytical Engineering. So today we will discuss the classification and preparation of fibers and understand the biodegradable polymers in this session as a part of engineering materials. So here are the topics. Fibers. There are two different types of fibers: natural fibers and synthetic fibers. Then fiber reinforced plastics. So this is a hybrid composite that is used in many of applications. Then biodegradable polymers. Its classification like biodegradable polymers, different polymers. Then advantages of these biodegradable polymers in the construction and other applications. Fibers. So fibers are a class that materials are continuous filaments and are called as discrete elongated pieces. These are the fibers. So they are crystalline in nature. They are crystalline and present both in animals and plants and animals. So these are used in textiles, making ropes, utilities, springs, etc., strings, etc. So if we see, for example, our clothing is nothing but made up of fiber. The ropes that we tie for drying the clothes are made up of fibers, and the utilities baskets, like baskets, then strings are nothing but again curtains or any other which are used for stringing purpose. So there are two types of fibers. Natural fibers and synthetic fibers. So what are natural fibers? See, natural fibers are obtained from animals and plants. For example, animals, wool, woolen clothing like sweaters, then silk, like silk clothing. So these are examples of animal originated natural fibers. Then in plants, cotton dressings, then linen also used in clothing material. So these are good examples for natural fibers. So we will see in detail. Then what are synthetic fibers? Synthetic fibers are of four types: rayon, nylon, polyester and acrylic. See, these are the synthetic fibers. So in polyester we have two different types of polyesters: terylene and PET. So these are the synthetic fibers that are man-made. So these are made by the man or modified natural fibers. So natural fibers are found from plants, animals and geological materials. So there are different types of natural fibers, like vegetable fibers, for example, cellulosic material. So even the corn has a fiber that is coming out of it. So that is an example of cellulosic fiber. So cotton, jute are examples for making the textiles, ropes, mats, paper bags, etc. So these are the vegetable fibers that are oriented from the plants. Then wood fibers. This is the strength. The wood fibers makes the strength of a plant is due to the presence of wood. So for example, if we have a plant, this is the stem. So stem is, after growth, it forms wood. So this is strength of any plant, which is making it to stand. So from this we can obtain fibers called as wood fiber. So this wood fiber or wood pulp is used in making paper, and wood fibers are made used in like a jute for making bags. Like what we are using, jute bags is nothing but the fiber obtained or the jute obtained from the wood fiber. The animal fiber, these are made from protein, pure silk, animal fiber, wool and hair. So if you see the silk also, silk is obtained from caterpillar through feeding on the mulberry. Then wool from the sheep and hair are some of the examples for the animal fibers. So spider silk is used in making bulletproof jackets. So these are the applications of animal fibers. Then mineral fibers are asbestos is a good example of mineral fiber. Mica and other minerals are also the mineral fibers that are used in different applications. So synthetic fibers, the other type of fibers are the synthetic fibers. So this type of fiber can be produced in large quantities and are cheaper when compared to natural fibers. So examples are pure silk. Pure silk is very costly when compared to nylon or polyester or PVC or polyethylene. So these are some of the synthetic fibers that are used. Then fiber reinforced plastics. So these are the composites that are used in different applications. So combination of a plastic material and solid fillers. For example, this is the polymer fibers and the polymer matrix when combined together forms fiber reinforced plastic. So these have different properties. The properties varies when this combination takes place. So we will see what that hard plastic is formed. So that will be having mechanical strength and impact resistance. So these are known as reinforced plastics. Then fillers are like carborundum, quartz and mica are used, which imparts or gives hardness and strength to that particular plastic. Then asbestos provide heat and corrosion resistance. If you see an example, these are the roofing material which we use for the roofing purpose. So when it is mixed with asbestos, it becomes hard. As well provides resistance to heat. It means it keeps the room cool and also avoids corrosion due to rain and the summer. So that is how it is very good application, like can be used in roofing purpose. The nature of polymers used in FRP, nothing but reinforced plastics. So what are the nature of polymers? So if we see the composition, 50% of this moldable mixture contains fillers. The fillers whatever we are using are about 50% of its overall composition. The addition of carbon black to natural rubber increases the strength by 40%. For example, we have a rubber from rubber tree. From tree we obtain, that is nothing but naturally we obtained rubber. So when it is mixed with carbon black, what happens? Strength increases. That is why we are using in the applications of tires. So it requires wear and tear resistance. So the property can be changed by adding carbon black to the natural rubber, which increases the strength of the rubber and can be used in the tire manufacture. In China clay, this is the China clay. In the picture we can see when it is added to PVC or Teflon material or the polymer, it increases the insulation property. Why we require to increase the insulation property? Because whenever we apply for the electrical appliances, it requires, it should act as an insulator so that it will be shock proof. Then when calcium carbonate is added to PVC, then they are used for insulation, for tubing, seat covers, wires and cables. So calcium, like similarly like China clay, when calcium carbonate is added to PVC material, it also increases the insulation property that can be used for the electrical purpose so that it will be shock proof. Then asbestos filled FRP is largely used in electrical appliances. For example, if you see in this hot summer, like coolers are made up of plastic material that is with asbestos, so that it is cool. Like when the appliance is running throughout the day, it keeps it cool and also shock proof. So this is how asbestos filled FRP is used. Then here is a good example, like it is good shock and thermal resistance or the heat resistance because it doesn't get heated up, and has good moldability, can be molded in different shapes, and dimensional stability and repairability. Like if we are molding in a particular shape, the shape will be stable and also can be repaired easily. Then applications, if you see the applications of fiber reinforced polymer, fiber reinforced plastics find an extensive applications in spacecrafts. So if you see in spacecraft, if we use these FRP, the weight of this spacecraft will be reducing when compared to other metals. So similarly in the aeroplanes, boat hulls. So if we use plastics FRP here, it also reduces the weight, but has good working, just like the other material we are using, like wood. Then acid storage tanks, these are the acid storage tanks. They are chemically resistant, so we can even use it for the acid storage. The motor cars, so most of the parts in the motor vehicles are made from the fiber reinforced polymer. And the building materials, when we use it for the building materials, we can mold it in different shapes and it is easier for the construction purpose. The melamine FRP is used in the insulation and making baskets. So these are the good examples of for reinforced plastics or polymers. And because why we are using low efficient to thermal expansion, so even if it is exposed to heat or sunlight, thermal expansion is lower, so we can use it happily. Then high dimension stability, the low cost of production. So when we compare with the metals or wood or any other concrete, the production cost is very low for the fiber reinforced polymers. Then good tensile strength, so it has similar or comparable tensile strength when with the conventional materials. And low dielectric constant, non-flammable, non-corrode and chemical resistant. So these are the good properties which help us in different application, as if we see here. Next comes the biodegradable polymers. So what are the biodegradable polymers? This is a trending polymer material that is today, because the lot of our oceans or seas are getting contaminated with the plastic material. So whenever the plankton or the animals or the living organisms take in that water, they get died. So that is why we are more trending towards biodegradable polymers, which are very helpful. Like the plastic will be degraded after its usage. So we will see in detail what is biodegradability. So it is defined as the ability of being chemical transformation by enzymatic action of bacteria which are capable of further degradation. It is nothing but we have a polymer, there should be some chemical reaction that is transforming its original structure to some other structure, so that it can be degradable. So that is done by enzymatic action of bacteria. So this is quicker degradation process wherein the nature itself is trying to degrade the polymers. So biodegradation of polymers not only eliminates landfills. What are landfills? Like when we are throwing the waste into the land, so the earth is filled up with the polymer waste or the plastic waste, which takes longer time for the degradation. So but also, so it eliminates. So if when the degradation is faster, it eliminates these landfills. And also compostable bags for collection of leaf and yard waste, which is nothing but these bags, wherever we are using, wherever we are seeing compostable bags, those can be used for collecting the leaf and yard waste, and therefore it will degrade itself and also degrades the waste and the leaves that are being collected. So if you see, so the disposable tableware, bio waste bags, then carrier bags, all these are green. When it is green, it is recyclable. When it is green, it is recyclable. So these polymers which degrade the enzymatic action of naturally occurring microorganisms and bacteria are called biodegradable polymers. So naturally they are getting degraded into the soil or the earth or water. So they are called as biodegradable polymers. So the first biodegradable polymer is the catgut, which was developed by Romans and used as a sutures that degrades as wound heals. So this is the suture, this is the needle, you bend needle. Then this is the suture that is used in stitching. So stitching. So these sutures degrades after the wound is healing, as the wound heals. So this is a very good example, and this is a first biodegradable polymer that was discovered. So how does this biodegradation takes place? So degradation in environment occurs in two ways: photo degradation or degradable polymers, or oxo-degradable polymers. So these are the different types of polymers depending on its degradation process in the environment. So what is photo? Photo is due to light or the sunlight, and oxo-degradation is nothing but in the presence of oxygen. So what happens whenever the polymer is exposed, biodegradable polymer is exposed to sunlight, there are some reactions taking place. So they will be converting to oligomers, dimers, monomers, and ultimately releasing some other gases. So it is nothing but it is breaking down the chains that are present, interlinks present in that particular polymer. Then when it is exposed to oxygen, oxidative degradation takes place. So this is a cycle that goes on. The oxygen will be included into the polymer chain, and the hydrolysis takes place, hydrolytic degradation. So slowly the degradation process occurs. So partially degradable or eventually biodegradable are not accepted. So if the material or the polymer is getting partially degradable, that is not completely degrading into the soil, are not accepted as biodegradable polymers. And also it is important to consider the intermediate products that are generated during biodegradation, that it should not be toxic. Then weight loss or molar mass reduction, mechanical property loss, measures of biodegradation is not accepted, because just losing the weight or reduction of the weight or molecular weight or loss of its mechanical property or structure is not said as degradation and is not acceptable. Then the other way is the composting. We see in market like compostable bags. So what are these compostable bags? So a natural process in which organic materials are decomposed to produce humus, a soil-like substance. So there is a natural process that is going on. If, for example, there is a plant, and this is the soil. This is the soil. This is the plant that is growing. So whenever we are watering the plant, the top layer of this plant, near this plant, the fallen leaves and the top layer of the soil are degraded by the microorganisms and other insects in the presence of water, and forms a layer on this original soil. So this is nothing but humus. Humus is also very important for a plant to have, because it grows very well in this environment. So this is a formation of humus. So let us see how this will help in composting. So in the composting process also, it occurs similarly. So principally operated by microorganisms, small insects, earthworms, and soil inhabiting organisms contributes in this degradation. So nothing but the composting occurs, the polymer that is present after its usage, when we throw into the soil, there is a process going on like composting. So therefore those bags or polymer are called as compostable polymers or compostable plastics. So, and what are the biodegradable polymers to have their basic requirements? So, production of non-toxic products, as we have discussed already, during its degradation, there should not be any toxic products that are producing. Then capable of maintaining mechanical integrity until degradation. So this is nothing but, if we see this bottle and the fork, they are getting degraded from day 0 to 45. So with time the degradation is taking place, but still there is the mechanical strength is still present at the second time period. So that is how the good mechanical strength should be present until it is degrading completely. So this is the complete degradation. And control the rate of degradation. So there should be a control on the degradation process, that eventually it degrades so that all the material of the polymer gets degraded. So what are the ideal characteristics of a biodegradable polymers? They should be biocompatible. It means the size, shape, surface and leachability of that particular polymer should be biocompatible. For example, if you see the leachable, there are some compounds leaching out of polymer, coming out or migrating. If we can say that migrating from polymer during its usage. So, for example, we are using biodegradable polymers for packing food material. So, whenever there are some compounds migrating from that polymer into the food, they should be biocompatible. It means it should not be toxic to the person that is taking in that food material. So, that is what we say leachability. So, leaching some compounds out from that polymer into the food matrix or the other material that is used for covering this with this polymer. So they should be bioabsorbable. So these are for this a good example is the sutures again. Like a degradability profile is important, like how much it is degrading, when it is degrading, what is the duration and all. Then reabsorption of degradation products. So during degradation there are products that are producing, like for example water, carbon dioxide, so on. So those should be reabsorbed into the human body if it is in the case of a sutures. So that is what is nothing but bioabsorbable. So they should not be toxic in nature at any cost to the application part. Then they should be bifunctional, both physical, mechanical and biological. They should have different functionalities so that they can be used in different applications. And they should be stable, like the polymer should be stable throughout its processing, development, sterilization, storage, and ultimately its application and its lifetime usage. Then this term biodegradation is limited to description of chemical processes that is taking place that alters the molecular weight or solubility. So ultimately what happens, degradation is nothing but breaking down its original structure. So what happens? Soluble. So solubility effects and the molecular weight ultimately affects because it is breaking down the original structure. So bioaeration, that is nothing but done by bioaeration, may be restricted to a physical process that results in the weight loss of the polymer. So a complete biodegradation occurs in three ways: enzymatic the degradation, then hydrolysis, which is having two different types, like bulk erosion and surface erosion, then combination of both, like enzymatic and hydrolysis combination. So these are the three different methods of biodegradation that is taking place for the polymers to degrade into the matrix. So what is an enzymatic degradation? So if for example this is the polymer n times, so polymer chain. So what happens, the first step is the cleavage of crosslinks. The crosslinks are generally hydrogen bonding. So these crosslinks will be separated like cleavage. So the chain will be open. So this forms the open chain structure. So that is how when it is having crosslinks, it is water insoluble. So when it is opening the chain without crosslinks, then it becomes soluble. Then what is the second step? Transformation of side chains. So we will be converting it to polar state. The chains will be converted to polar state by adding some groups so that it becomes water soluble. So that degradation takes place. Then the cleavage of backbone. The ultimate cleavage is the cleavage of this main bonds that are between the monomeric units. So when it is cleaving the main backbone, then it will become the solubility. Solubility increases. So that is how there is an enzymatic reaction or the process that is going on. So there are different types of enzymes that are in action which are leading to this cleavage of bonds and ultimately degrading the material. Then the other type is the hydrolysis. In hydrolysis what happens? bulk erosion and surface erosion. In surface erosion, if you see, this is the polymer, complete polymer, there is an erosion at the surface, only at the surface, so the degradation is low degradation occurs. When it is bulk erosion, if this is the polymer, upon increasing with time, there is erosion in the bulk state of that polymer and ultimately gets degraded. High degradation takes place. So in bulk degradation, most of the polymer gets degraded. So examples are bulk degradation, polylactic acid, polyglycolic acid. And in surface degradation, which polymers undergo surface degradation? They are polyanhydrides and polyautoesters. So these two types of polymers undergo surface erosion. Then there are different types of biodegradable polymers, natural and synthetic. So what are natural polymers? They are obtained from natural based polymers like collagen, albumin, gelatin. These are some of the examples. Then polysaccharides are already present in the nature. So chitosan, agarose, cellulose and dextran. These are some of the examples for the natural polymers. And synthetic polymers are the man-made polymers or modified polymers. So these are partially degradable, and the examples are polyesters. In polyesters, polylactic acid, polyglycolic acid and polycaprolactone. So these are the examples for the polyesters. Then polyanhydride, so polyadipic acid, polycybic acid, polyethylene terephthalate is example for the polyanhydride. Then polyamides, so polyamino acid, polyamino carbonate. Then in phosphorus, polyphosphates, polyphosphonates, polyphosphazine, polyether, polyethylene glycol, polypropylene glycol. So in the view of our syllabus and the Btech state, so we will be discussing PLA and PVA. Polylactic acid, polylactic acid and polyvinyl acetate. Polyvinyl acetate. So we will see the examples in detail. So the polymers which are found in nature and are grown due to the growth cycles of all the organisms are nothing but natural polymers. What are natural polymers? They are formed in nature during the growth cycles of all the organisms. For example, we have glucose in our body, which is nothing but a type of polymer. So in connection, when it is connecting together, it forms a polymer. So for example, polysaccharides such as starch, cellulose, these are the polysaccharides that are already present in nature in all the organisms. And there are four groups of naturally occurring biodegradable polymers. Polysaccharides are starch, cellulose. Then proteins are like gelatin, casein, silk, wool. Then polyesters are polyhydroxy alkanoates. Then others are like lignin, shellac, natural rubber. So these are the good examples of different types of naturally occurring biodegradable polymers. So these are from the plant origin and animal origin and microbial origin. So these are the examples of different natural polymers that are present in the nature. Then comes the synthetic biodegradable polymers. What are synthetic polymers? They are man-made. So they are produced from the chemicals or biological sources. So they are also biodegradable in nature. So there are some types of synthetic polymers we will be discussing. For example, polylactic acid or polyactide. It is a biodegradable polymer which is thermoplastic polyester belonging to polyhydroxy alkanoids. So these are the group. It belongs polyhydroxy alkanoids derived from renewable sources such as tapioca starch. Tapioca starch, this is the tapioca starch fruit, that is, then this is the starch obtained from the fruit. So, or sugarcane possesses the following structure. So, it belongs to polyhydroxy alkanoids and it is obtained from either from the tapioca starch or sugarcane molasses. So it has the structure PLA PLA, polylactic acid. So for example, here we can see the sugar cane. This is the sugar cane obtained from the crop. Then after processing, this is the lactic acid that is obtained, or the lactic acid, lactate that is obtained, and on polymerization it gives polylactic acid. So these are further used in different applications like covers, or used in wrapping food material, mostly wrapping food material. So these are the roles, and these are some packing containers. So this is the example for polylactic acid. So what are the properties? What happens when polylactic acid is forming? So the glass transition temperature of polylactic acid is 60 to 65 degrees centigrade, and the melting point is 173 to 178 degrees centigrade. So it has a high melting point, therefore we can use it for food and other purposes. And this is a chiral compound existing as poly-L-lactic acid. So there are two different compounds that is present in the organic matter, like chiral compounds. So poly-L-lactic acid, it is a poly-L-lactic acid. It is a chiral compound for that. Then applications, they are used mostly in the medical implants like anchors, screws, pins, mesh. These days we have seen lot of medical applications like implants that are going on. Even a tooth is broken, we can implant back. So for example, this is the screw that is made from the polylactic acid, mesh, then hip plates. So these are some of the examples. Those can be used in different medical implants. Then for making compostable packing material, disposable garments, then good food packing. So compostable packing is nothing but whenever we pack the material or the food material, after we throw out into the waste, they get compostable. So we have already seen the definition and its working principle. So disposable garments are nothing but we can use it for once usage. So once it is used, they can be thrown back, so they are used, they can be degraded easily. So these are made from the polylactic acid. So this is the container that is used in the food packing, and also the rolls sheets that are used in packing for the materials and during transportation. So these are the good examples for polylactic acid. Then the other one is the polyvinyl acetate, which is a synthetic polymer, which is also a water soluble polymer that is used, a biodegradable polymer having excellent mechanical properties and compatibility with starch. So this is the structure, polyvinyl acetate. This is the vinyl structure and the acetate group attached. So it is forming N times is nothing but polyvinyl acetate. So that is the innovative biodegradable polymer that is forming from starch. So what happens when the starch it is natural source, but we are making natural from the natural source, but chemical reaction, we are inducing some chemicals, so it is a modified natural one, therefore coming under synthetic polymer. So we are using some chemicals for making the polyvinyl acetate, so therefore it is becoming synthetic polymer, but however it is biodegradable, completely biodegradable, totally biodegradable in a wide variety of environment. So we can use in different applications so that it gets dissolved and degraded easily. It can be hydrolyzed to glucose by microorganisms or enzymes and then metabolized to carbon dioxide and water. It means after its usage, for example, if we are packing for food, after its usage, even if we throw back to the earth, it will be hydrolyzed to glucose first. Once it is forming glucose, it is very easy for its degradation. So this conversion to glucose is done by microorganisms or enzymes and then metabolized to carbon dioxide and water. So how the polyvinyl acetate is manufactured or produced? So it is produced from the acetic acid and acetaldehyde produced from molasses. So how is it? Like for example, this is the starch or the carbohydrates like glucose, cellulose or starch on hydrolysis will form lactic acid, and the second step on oxidation step with copper oxide, it gives acetic acid. So this acetic acid in the presence of acetaldehyde will be forming polyvinyl acetate. Polyvinyl acetate. So this is the formation of polyvinyl acetate. So what are the properties of this polyvinyl acetate? They belong to vinyl polymers. So with the name itself, we can understand that they belong to vinyl polymers and are water soluble. Then excellent mechanical properties. So if we see this picture, polyvinyl acetate, upon hydrolysis, it is forming polyvinyl alcohol. So hydrolysis, it takes place hydrolysis. So therefore, it is very soluble in water. So if you see this picture also, water soluble bags, when it is dipped into the water, it got dissolved. So it is compatible with starch, that is starch mold can be introduced in the backbone for quick biodegradability. So it also helps in biodegradation. So what are the applications? Polyvinyl acetate is used in food industry as a packing material, then food storage, catering and compost bags. So these are some of the examples wherein, see for example, if you see this bag is already named with polyvinyl alcohol, so upon hydrolysis it gets degraded easily. So even if we throw in water like seas, oceans, beach, etc., they can be degraded very easily. So no harm to any plankton or animals. Then the advantages of biodegradable polymers, they are very advantageous. So the localized delivery of drug in medical field, the localized delivery of drug is very important. So whenever we are imparting a drug, there is specific site or the organ which requires this drug to be sent. So these polymers will help in localized delivery of drug. Even if it is the polymer, it gets degraded after its duty is done. Then sustained delivery of drug, then stabilization of drug, decreasing the dosage frequency, then reduces side effects. So because of these degradability property, the side effects will be reduced. Then improved patient complaints, like a patient will be very confident in usage. So then controllable degradation rate. So even if the organ is, when the organ starts growing after its implantation, this polymer gets degraded slowly. So there is control in the degradation rate. So it is used most. So these are the application. If you see this picture, drug delivery, cardiology, invascular scaffolds, artery diseases, then orthopedics like bone repair or medical implants like plates, then others are like sutures, pediatrics, periodontal surgeries, tissue engineering. In tissue engineering, the polymer mesh itself is kept into the body so that it acts as a tissue. So property of the tissue is regained. So these are the good examples for medical field applications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.